At exactly 4:42 in the morning on November 22nd, something happened that no space agency wants to talk about. China's Tianwen-1 orbiter, while passing behind the interstellar object known as 3I Atlas, picked up something strange. Not a signal, not a flare, a pulse, rhythmic, structured, perfectly spaced. The plasma in the tail wasn't reacting to solar wind. It was generating its own timing. And then, total silence. Not from the instruments, from the world. NASA said nothing. ESA quietly declined to comment. China. They scrubbed the raw data from their public logs in under 12 hours. So here's the question. Why is an interstellar comet behaving like a system? And why is everyone pretending it didn't happen? You're watching 3I Atlas, a deep space anomaly that's forcing even veteran scientists to reconsider what a comet can be. Before we dive in, drop a comment with two things. Where are you watching from? And what time is it right now in your part of the world? Yes, we're tracking locations, and yes, even someone in Antarctica checked in last week. And if you're watching from orbit, go ahead and blink twice. We'll take it from here. While you're at it, don't forget to subscribe if you want more of these breakdowns. Unfiltered, data first, and without the hype. We publish real documents, real events, and strange space stories that others won't touch. Now take a slow breath. Let's walk through the facts, calmly, clearly, and without jumping to conclusions. At precisely 4:42 a.m., on the morning of November 22, 2025, China's Tianwen-1 orbiter crossed into the observational shadow of 3I Atlas, positioned perfectly behind the object's plasma tail. What happened during those next few minutes was subtle, quiet, and almost invisible. But for scientists tuned to the right instruments, it was as if something exhaled, slowly, rhythmically, and intentionally. The orbiter's Langmuir probe, a device typically used to measure local plasma conditions such as electron temperature and density, began registering a faint but repeating signal. Oscillations in plasma density that came in perfect intervals. Every 23 seconds the readings spiked, then returned to baseline, then spiked again. In total, 8 clean pulses were recorded over a window of just under 4 minutes. No interference, no drift. Just 8 identical curves on a chart, each rising with the same slope, the same duration, and the same decay. In the language of instrumentation, this is not random noise, this is structure. Now, Langmuir probes do not detect light or electromagnetic radiation the way a traditional radio telescope does. They listen to the local weather of space, the ionized gas swirling through the solar system, known as the solar wind. So what Tianwen-1 picked up wasn't a signal in the communication sense. It was a pattern inside the ionized tail of 3I Atlas. A physical heartbeat, not a broadcast. Here's why this is so strange. Plasma tails from comets don't behave this way. Normally, a comet passes close to the sun, heats up, and begins to shed material. That material, mostly water vapor, carbon monoxide, dust, is ionized by solar ultraviolet light and swept backward by the solar wind. The result is a broad, soft, irregular fan of charged particles. It's messy, it's turbulent, it looks like steam coming off a boiling kettle. But 3I Atlas doesn't appear to be boiling, it appears to be humming. The pulse pattern didn't match anything expected from solar wind turbulence. Solar wind density is chaotic, shaped by magnetic interactions from solar flares and coronal mass ejections. But on November 22nd, there were no solar storms, no flares, no solar windshock fronts. The space weather that morning was uneventful, calm, boring, which makes the detection even more significant. One immediate hypothesis is that the pulses were driven internally by the object itself. That idea challenges our basic assumption that 3I Atlas is a comet, because for a comet to produce a regular pulse in its plasma tail, something inside it must be driving the cycle. A rotating jet? Possible, but no known cometary jet pulses at 23-second intervals. A cavitating pressure buildup in an internal chamber? That would require structural integrity and a kind of internal regulation we've never seen in a frozen rock. Another explanation is that we're witnessing a kind of resonance, an oscillation caused by the interaction between solar magnetic fields and a conductive object. But even that theory leads to uncomfortable questions. To resonate with magnetic fields, the nucleus would need to be at least partially metallic, and if 3I Atlas is even partly metallic, then it's not a comet, It's something else. It's worth repeating. This signal was not a broadcast. No one is suggesting this is a message. But when a lifeless object pulses, repeats, and does so only when a probe is directly behind it, the symmetry is hard to ignore. What adds to the mystery is what happened after. China pulled the telemetry within hours. The waveform graphs disappeared from public scientific dashboards. All that remained was a single thermal image, scrubbed of timestamps. There was no press conference, no denial, no analysis, and perhaps that's the most telling signal of all. Because when scientists fall silent, when even raw data vanishes, it usually means one thing. Something was seen that no one can yet explain. And until they can, no one is allowed to speak. So for now, we're left with a pulse. 8 simple curves, quiet, regular, impossible to dismiss. And one lingering question. What kind of object pulses from its tail? In the most basic terms, a comet's tail is an accident, a side effect, a natural response to heat and pressure. When sunlight strikes the surface of a comet, frozen volatiles, mostly water ice, carbon dioxide and other gases, begin to sublimate. That means they shift directly from solid to gas, skipping the liquid phase entirely. The gas escapes the nucleus and drags tiny dust particles with it, forming what's known as a coma, a glowing atmosphere surrounding the comet's core. As solar radiation continues to push on that coma, and as charged particles from the solar wind interact with it, the escaping material stretches out into space, forming the classic tail. But here's the thing. This tail should always behave like smoke in the wind. Irregular, fuzzy, reactive. It should shimmer with entropy. In every comet we've studied, that's what we see. Broad arcing tails that bend in real time depending on their angle relative to the sun. Some comets even split into 2 tails, one made of dust, the other of ionized gas. And each of those tails behaves differently. The dust tail curves gently along the path of the comet, while the ion tail points directly away from the sun, straight and narrow, shaped by the constant flow of solar wind. None of them pulse, and none of them hold a shape against solar pressure. That's why the behavior of 3I Atlas is so disturbing. When Tianwen-1 flew behind the comet on November 22nd and detected plasma pulses travelling through the tail, it broke one of the quiet rules of space weather. Tails aren't supposed to do anything. They are supposed to happen. They are passive, reactive. They are consequences, not causes. But the pulses inside 3I Atlas's tail suggest that this object is not merely responding to sunlight. It's regulating something, internally, repetitively. That changes the framing entirely. To be clear, this is not about aliens. It's about physics. Let's imagine a regular comet moving toward the sun. As it heats up, gas erupts from its surface in short-lived jets, creating bright spots in the coma and eventually feeding the tail. These outbursts are random, driven by surface composition and rotation. They happen where sunlight hits, or where volatile pockets collapse under pressure. There is no rhythm, no pattern, just sublimation and pressure escape. Now compare that with what we've just seen, a tail that pulses at fixed intervals, a tail that holds its structure even after perihelion, when the object is supposed to be cooling down, not waking up. Why would that happen? There are a few natural theories. Some researchers propose that internal caverns inside 3I Atlas may be creating pressure chambers. When gas builds up, it vents explosively through specific surface points. But even this scenario falls short of explaining the precision of the pulses. Natural geysers don't operate like clocks. Others suggest it could be a resonance effect, that perhaps magnetic field lines from the sun are somehow coupling with conductive material inside the comet, creating plasma oscillations. If true, that would imply 3I Atlas has structure. Not just rock and ice, but something more cohesive, something metallic or stratified enough to resonate. Again, that's not typical of a comet. It's worth noting that the tail's coherence also violates energy expectations. If the object is no longer shedding high amounts of mass, the tail should dissipate. Instead, it's maintaining shape, like a jet stream rather than a smoke trail. This leads to an uncomfortable possibility. The tail may not be a passive structure at all. It may be functional, an active process, a kind of exhaust, not from a rocket, but from a system we haven't yet identified. For now, we have to go back to first principles. What is a tail supposed to do? Scatter. What is this tail doing? Pulsing, holding, directing. That doesn't sound like an accident. It sounds like intent. In the hours immediately following Tianwen-1's pass behind 3I Atlas, the data was routine. Until it wasn't. At 04:42 am, local time on November 22nd, the orbiter's Langmuir probe registered structured pulses within the comet's plasma tail. Not a single glitch. Not solar interference. Structured oscillations in plasma density. 8 pulses, evenly spaced, like waves rolling through a quiet ocean. Within 6 hours, China's National Space Administration, CNSA, removed the original telemetry logs from its public-facing data repository. No explanation, no error message, no retraction. Only one data product was left behind, a filtered thermal image, no raw telemetry, no timestamp, no waveform, nothing that could be analysed by outside physicists. And that silence? It echoes louder than a press conference. Let's be clear, China's space agency is among the most technically advanced in the world. Tianwen-1, though best known for its Mars work, was equipped with one of the most precise Langmuir systems ever flown on a deep space mission. It wasn't luck that caught the pulse, it was planning, and that makes what followed even more chilling. Because when agencies pull data like this, it's usually for one of 3 reasons. First, contamination. The data was corrupted and is undergoing internal review before public reposting. But insiders on Weibo and secondary university channels confirmed the original waveform passed multiple verification steps. It wasn't noise, it wasn't a misread. Second, classified crossover. Some space assets serve both civilian and military purposes. If the pulse resembled something sensitive or interfered with national security protocols, the dataset could be withheld. But the pulse was detected in the deep tail of a comet, 300 million kilometers from Earth. This wasn't a spy balloon. It wasn't a threat. It was a plasma wave in deep space. And third, they don't know what it was. That is the most likely reason for silence. Because saying we don't know in public means triggering global headlines. It means opening a scientific door without knowing what's behind it. And in international space politics, admitting you've detected something unexplainable often leads to finger-pointing, not collaboration. But there's more. Independent observers noted that 2 of China's Earth-based deep space antennas, one in Kashgar and one in Qingdao, were quietly retasked to observe 3I Atlas during the same window the pulse was detected. These ground stations were not scheduled to track the comet. They were scheduled for lunar comms and routine deep space monitoring. That schedule changed, which means whatever Tianwen-1 saw, Beijing wanted confirmation. From Earth, from multiple baselines. And yet, not a word to the scientific community. The International Astronomical Union, IAU, has received no official pulse report. The Jet Propulsion Laboratory, JPL, has not revised their Atlas model, and the only reference to the event exists in the metadata of one now sanitized spectrograph file, where 8 timestamps have been redacted. All of this paints a strange picture, not cover-up, but caution. China is not hiding a discovery. They're buying time to understand it. That's not malicious. It's strategic. But it leaves the rest of us staring into a data vacuum, listening to the silence and asking the only question we can. What could make a space agency this precise go dark? Was it a mechanical resonance? An internal chamber releasing plasma in clockwork rhythm? Was it evidence of a guided system? Something regulating gas flow like an exhaust valve? Or was it simply too strange to name? The absence of information leaves room for imagination, and in that vacuum, every theory, natural or not, can flourish. For now, all we know is that the most detailed readings ever captured inside an interstellar tail are locked in a Chinese database, scrubbed of public access and filtered through silence. The pulse happened, they saw it, and now they're not speaking, and sometimes the silence is the anomaly. Let's begin with what it wasn't. The pulse detected by Tianwen-1 was not a radio transmission. It wasn't a beacon. It wasn't a coded message. It wasn't light, sound, or any form of electromagnetic radiation. It wasn't even energy in the traditional sense. What it was stranger, and possibly more telling. The pulse was a plasma density oscillation. To understand that, you need to think about space not as a vacuum, but as a medium. The solar system is filled with plasma, charged particles streaming from the sun at hundreds of kilometers per second. This soup of electrons and ions fills the space between planets. It's chaotic, turbulent, loud, in the language of sensors. But on November 22nd, inside the tail of 3I Atlas, that turbulence momentarily became music. Tianwen-1's Langmuir probe, a device designed to measure electron densities in a surrounding plasma environment, began registering spikes in its readings. Not one, not two, but 8 spikes spaced evenly, each lasting just under a second and occurring every 23 seconds. That number, 23, is important. Not because it's mystical, but because it's mechanical. Plasma oscillations driven by solar. Wind are random. They swirl, collide, fragment. They don't arrive on a schedule, but these pulses did, which implies a driver, something internal, something with timing, something with structure. Let's run through the possibilities. Possibility 1. Thermal venting from internal pressure. As a comet approaches the Sun, its subsurface gases heat and expand. When pressure builds behind crust layers, it can rupture, like a geyser. That might cause temporary jets. But would they pulse every 23 seconds? No, and certainly not 8 times in a row without deviation. Geysers don't run on clocks. Possibility 2. Rotational jetting. If the comet is rotating and it has an active vent on its surface, then every time that vent rotates to face the Sun, it might release a jet. This is more plausible. But it would mean the comet is spinning once every 23 seconds. That's incredibly fast. Not impossible, but unlikely. The average rotation period for comets ranges from hours to days. A 23-second rotation would require immense cohesion, far more than we've seen in a fragile, loosely bound object. At that speed, centrifugal forces would tear a normal comet apart. So unless 3I Atlas is denser and more cohesive than any known comet, possibly metallic, this explanation doesn't hold either. Possibility 3. Magnetic resonance. Here's where it gets stranger. If 3I Atlas contains metallic materials, like nickel or iron, it could in theory interact with the solar magnetic field. This could produce a form of induced oscillation. In laboratory plasma physics, we call these Alfvén waves, low-frequency oscillations that travel along magnetic field lines. But Alfvén waves are usually small and chaotic, not crisp, repeating pulses, and they require a stable field environment. The solar wind is not stable, it's messy, and it doesn't pulse every 23 seconds, which leaves us with the possibility no one wants to say out loud. Possibility 4. Internal modulation. Something inside 3I Atlas, either mechanical or resonant, produced the pulse. Not a signal, but a symptom, as if the comet has compartments, chambers, valves, some internal structure that allows energy to build, release, and reset, again and again. This doesn't mean the comet is artificial, but it does mean it's not behaving like rock and ice. It's behaving like something that can hold pressure, that can cycle, that can breathe. Because structurally that's what the waveform looks like. A breath, a rhythm, not static, not chaos, but something between the two. And here's one final detail. The pulse stopped. After those 8 bursts, roughly 3 minutes and 4 seconds, it ended. The probe returned to baseline readings. No decay, no trail, no follow-up wave. Whatever happened, it was finite. Not decaying turbulence, not a solar interaction, a single, isolated burst cycle. That suggests it wasn't random. It was timed, and whether that timing was biological, mechanical, or something in between, we simply don't know. But in deep space, when something pulses once and never again, it forces a question. Was it accidental? Or was it deliberate silence? While Tianwen-1 drifted behind 3I Atlas and recorded plasma pulses echoing through the comet's tail, something strange happened back on Earth. Nothing. No observatory, optical, radio, or infrared, reported a matching detection. Not in Chile, not in Hawaii, not in South Africa, not even from SOHO or the Solar Dynamics Observatory. Across the globe, hundreds of telescopes were tracking 3I Atlas during its post-perihelion glide, and not a single one recorded the pulse. To the untrained eye, this might seem like confirmation bias. If it was real, the skeptic might say, wouldn't we have seen it from Earth? But the truth is far more interesting. We didn't see it from Earth because Earth was in the wrong place. Tianwen-1 was in a rare observational position, behind the plasma tail, aligned along the anti-sunward axis. From its orbit, the spacecraft was downstream of the ion flow, in what scientists call the plasma wake. Imagine standing behind a speeding car and feeling the turbulence swirl around you. That's the region Tianwen-1 entered. But from Earth's perspective, we were effectively staring at the comet's nose. Our telescopes were facing the sunward side, where sunlight hits gas vents and nothing unusual appeared. The pulses detected by Tianwen-1 were flowing away from the sun and thus away from Earth. In plasma physics, direction matters. Charged particles follow field lines and pressure gradients. They stream along paths carved by solar wind and magnetic structure. From Earth's angle, that structure was invisible, like trying to hear someone whisper while they're facing away from you in a storm. Even our most sensitive instruments, like LOFAR in the Netherlands, or the Very Large Array in New Mexico, weren't equipped to detect the kind of density modulations Tianwen-1's Langmuir probe was built for. Earth's magnetic field and ionosphere block many of the fine plasma readings that spacecraft can observe in situ. And so, from Earth, we saw a quiet comet, still glowing, still active, still drifting past the sun like any other interstellar object. Meanwhile, 300 million kilometers away, Tianwen-1 picked up what can only be described as an invisible heartbeat. Here's another complication: timing. The pulses occurred in a tight 3-minute window, at a very specific orbital position. If a ground-based observatory had happened to be looking at the tail, not the coma, not the nucleus, through a narrowband radio spectrometer and filtering out solar noise and accounting for Doppler shifts, they might have seen a fluctuation. But no one was watching that slice of space in that way, at that moment. It's the classic curse of astronomy. You only see what you're looking for. And no one expected a comet tail to pulse. No one predicted 3i Atlas would behave like an emitter, because tails aren't supposed to be transmitters. They're leftovers, trash trails of gas and dust. At least that's what we thought. And yet, here we are, with the most advanced Earth-based array network silent, while one orbiter in a precise plasma shadow catches something we cannot explain. This creates an uncomfortable asymmetry in the data record. We have a detection, but only in one location. That asymmetry is why so many scientists are hesitant to speak out, because in science, a signal detected once, by one instrument, without confirmation, is dangerous. Not because it's wrong, but because it forces you to choose. Either chase the anomaly, or play it safe and ignore it. And ignoring it is tempting. Because if we admit that Earth missed something, that our entire planetary fleet overlooked an interstellar object pulsing, then we're forced to ask an even darker question. What else have we missed? Let's ask the simplest question first. Could the pulse be natural? On the surface, the answer seems like yes. Plasma, after all, is inherently unstable. It ripples, it dances, it writhes in ways that seem unpredictable. In both laboratory settings and deep space environments, we've seen waves form, collapse, and recombine. Plasma physicists deal with instabilities every day. Kink modes, mirror modes, drift waves, and the infamous Kelvin-Helmholtz instabilities that form when two streams of plasma shear past each other. So maybe what Tianwen-1 saw in the tail of 3i Atlas wasn't an anomaly, just nature, doing what nature does best, creating chaos. But there's a problem. What was detected on November 22nd wasn't chaos. It was rhythm. It was order. It was 8 clean pulses, spaced at 23-second intervals, each with a sharp rise and fall time, and no detectable decay. That kind of signal, structured, symmetric, and limited to a finite window, isn't what natural plasma instabilities typically produce. Let's take a closer look. Kelvin-Helmholtz instabilities, for instance, are beautiful in simulation. They appear as roiling vortices, like swirling curls of cream in coffee. They require velocity shear between two plasma regions, say, the solar wind and a comet's outflowing gas. But these instabilities are continuous and broad spectrum. They create eddies, not pulses, and crucially, they don't stop after 8 oscillations. Alpha N waves, oscillations of plasma caused by magnetic tension, are another candidate. These can travel great distances along magnetic field lines and are often seen in Earth's magnetosphere. But again, their waveform is sinusoidal and often chaotic over time. And while alpha N waves can be coherent under some conditions, they are sustained, not abruptly limited to a 3-minute episode. Some scientists have floated the idea of ion acoustic waves, Pressure waves in plasma similar to sound in air. These could theoretically form in the comet's tail as solar wind particles interact with ejected gas. But the problem remains. Ion acoustic waves aren't known for producing consistent periodicity with fixed timing. They ripple, they decay, they're messy. So if the pulse from 3I Atlas were a plasma instability, it would have to be an entirely new kind, one not yet described in literature. Now let's talk about symmetry. Nature doesn't often do symmetry unless something forces it. Supernovae explode asymmetrically. Storms form off-center. Even planetary orbits, while orderly, are elliptical, slightly broken, slightly imperfect. But the pulse in 3I Atlas's tail was clean, not just repeating, but measured, the kind of signal you'd expect from a lab-controlled experiment, not a chaotic dust cloud. There's another layer to this puzzle: directionality. Plasma instabilities generally propagate in all directions relative to their source. They're messy and volumetric. But what Tianwen-1 detected came in a beam. The pulses travelled tailward, away from the Sun, along a narrow stream of plasma. That's not typical. It implies either a collimated source or an environment that's shaping and containing the oscillation as it travels. Which raises the obvious counter-question: could this be artificial? Not necessarily in the science fiction sense, but in the sense that something internal, perhaps mechanical, perhaps geological, was regulating an outflow, like a geyser with a blocked chamber, or a pressure valve that releases in clockwork rhythm. Those are not normal in comets. But then again, 3I Atlas isn't normal. At some point we must confront a threshold. The line between natural and unnatural isn't always sharp. Some patterns begin as chaos, then resolve into order. Others begin as order, then break apart. But when a system starts ordered and then shuts off, that feels different. Plasma instabilities don't switch on and off like machines. They grow, they saturate, they fizzle, but they don't start perfect and then vanish. So could it be natural? Yes. But if it is, it's something we've never seen before, and that means the universe just taught us a new trick. One of the most troubling aspects of the November 22nd detection is something that, at first glance, seems unrelated to the pulse itself. It's the shape of the tail, or rather, the stability of that shape. Normally, a comet's tail is a byproduct of mass loss. As sunlight heats the comet's surface, volatile compounds sublimate, turning from solid ice into gas. That gas carries dust and other debris outward, forming a glowing coma around the nucleus. Solar radiation and the solar wind then push this material back, forming a tail that always points roughly away from the Sun. It's beautiful, chaotic, and thoroughly predictable. But 3I Atlas is breaking that rule. Images captured by Chinese, European, and amateur astronomers show a tail that is unusually thin, tight, and coherent, stretching hundreds of thousands of kilometers across space in a laser-like stream. This would normally imply extreme mass ejection, a colossal amount of material being flung outwards in a continuous violent stream. But that's not what we're seeing. Photometric models show that 3I Atlas is not shedding mass at an extraordinary rate. In fact, its outgassing has decreased since perihelion. Instruments from JPL, the Subaru telescope, and the Swift UV telescope show no evidence of large volatile surges. There's no flood of carbon dioxide, no visible fragmentation, no plume that matches the size and stability of the tail. And that's the paradox. If the tail is this structured, this extended, and this uniform, it should require a corresponding amount of mass to sustain it. But that mass isn't leaving the nucleus, at least not in the volumes required. Let's put that into perspective. A tail of this length and narrowness, maintained over days, implies an active flow of charged particles, ionized gases, at high velocity. Under standard cometry models, that would require the release of tens of thousands of tons of material per hour. Not dust, but gas. And yet, the observed spectrum shows no such densities. The dust-to-gas ratio is low, the brightness hasn't spiked, and most importantly, the tail hasn't fragmented or diffused. This leads to an unavoidable conclusion. Either the tail is being sustained by far less mass than physics allows, or we're missing something about how that mass is being used. One possibility is that the tail isn't being shaped by mass at all, but by structure. That is, instead of a cloud of material pushing outward randomly, we're seeing a guided flow, channeled, maybe even regulated. In spacecraft propulsion, Something similar happens in ion drives. Small amounts of mass are accelerated electrically to high speeds, producing a narrow continuous thrust. The total mass ejected is tiny, but because it's controlled, it creates a beam. The tail of 3I Atlas is beginning to resemble that more than a traditional comet. Narrow, low mass, and structured. That raises a second possibility: internal architecture. What if the interior of 3I Atlas is not a chaotic rubble pile like other comets, but a stratified, organized body? Something that can control how and where gas vents, concentrating it into specific outflows rather than random jets. If the object has internal chambers, regions of trapped volatiles separated by barriers, then outgassing could occur in clean, rhythmic bursts rather than chaotic explosions. And if those chambers are reinforced by mineral layers, or even metallic veins, that would change the physics entirely. A structured interior would mean the comet's behavior is regulated not just by heat, but by design, whether geological or otherwise. In either case, the core problem remains. The shape of the tail doesn't match the amount of material we're seeing. Something is holding it together, and if it's not mass, then it's method. Every comet tells a story not just in its path but in its debris. Behind every active comet there's usually a quiet turbulence, a chaotic cloud of fine particles and volatile remnants that trail behind the main tail. It's not as elegant as the glowing ion stream, but it's just as important. Scientists call it the secondary wake, the diffuse footprint left behind as the comet continues on its way. But in the case of 3I Atlas, that wake is missing. Let's break this down. When a comet ejects material, it doesn't do so with perfect efficiency. The primary tail is shaped by solar radiation and magnetic interactions. It pushes material away from the sun. That's the big, visible streak. But not all ejected matter obeys that flow. Some of it lingers. Some of it curls behind in the orbital path, forming a slower, less structured tail. Think of it like exhaust haze behind a jet engine. That's the secondary wake. We see this in every major comet. Halley, Hale-Bopp, Neowise, even Oumuama's less visible acceleration left a haze of particle dispersion. But for 3I Atlas, nothing. No diffuse trail, no particulate cloud, no scattering behind its path, just one clean structured plasma stream. And that's not how comets behave. If anything, the absence of a wake raises more questions than the pulse itself, because in the language of orbital physics, nothing is a signal. Let's imagine a natural explanation first. Perhaps 3I Atlas is composed almost entirely of volatiles, materials that, when heated, sublimate completely into gas, leaving behind no dust. If it had very little rocky or carbonaceous content, it might leave no particulate trail. But this scenario is rare. Even the iciest comets carry dust, microscopic silicates and minerals embedded in the ice from their formation. Sublimation may strip them clean, but it doesn't erase them. Another possibility is that the tail is being shaped not by random ejection, but by directed expulsion. In this theory, outgassing is funneled through tight channels, ejecting only specific types of ions at high speed. This could explain the narrow sustained beam observed in images, and the lack of leftover debris. But that also suggests an internal structure that we don't associate with natural comets. To channel outflow like that requires cohesion, porosity, and possibly design. Let's consider the third option. What if the wake exists, but it's been pushed out of view? Solar wind pressure exerts force on ionized particles. If 3I Atlas's tail is unusually aligned or interacting with a magnetic field loop, it's possible that the trailing particles are being swept aside, carried perpendicular to the comet's trajectory, but this would still leave some trace in the data. Yet infrared and ultraviolet observations show no such cloud, no lateral scattering, no drift. This leads to a possibility that makes scientists deeply uncomfortable. What if the tail is all there is? What if every gram of expelled material is accounted for in the primary beam, leaving nothing behind? That would imply a closed system, a level of energy efficiency we don't associate with random outgassing. A system where the comet isn't leaking material, it's using it. That's not how comets work. That's how propulsion works. We're not saying 3I Atlas is a spacecraft, but the lack of a secondary wake forces us to consider a radical idea, that this is not just a natural process, that the object is ejecting material in a way that is deliberate, directional, and highly optimized. In spacecraft engineering, we calculate specific impulse, the amount of thrust per unit of mass ejected. High specific impulse systems leave behind minimal residue, just a clean vector of force, and that's what we're seeing here. A clean beam, no drift, no dust, no wake. The silence behind 3i Atlas is louder than any signal, because it's not just what the object is doing, it's what it isn't doing, and nature doesn't usually waste that kind of opportunity. NASA has a reputation for communicating, especially when comets are involved. When Oumuamua passed through in 2017, they held press conferences. When Comet Neowise lit up the sky in 2020, they issued daily briefings and shared raw data across their public-facing APIs. But with 3i Atlas, something's different. Despite the object's abnormal tail structure, unexplained plasma pulses and missing secondary wake, NASA has said virtually nothing. And in this case, that silence speaks volumes. Let's start with what we do know. NASA continues to track 3i Atlas. Its orbital elements are updated regularly on JPL's Horizon system, which publishes the comet's trajectory, distance, and speed. That suggests observation hasn't stopped. They're watching. But the how and why of what they're seeing, that's been scrubbed of commentary. There are no white papers, no press statements, no community updates from the Planetary Defense Coordination Office, the Infrared Telescope Facility, or any of the usual channels. Even when Tianwen-1's pulse detection leaked through secondary scientific circles, NASA didn't acknowledge the event. They didn't refute it. They didn't explain it. They just stayed quiet. Now, there are a few explanations for this. Explanation 1, there's nothing to say. Perhaps NASA simply doesn't have the data. Maybe their instruments weren't aligned for this type of detection. That's plausible. Most of their spaceborne assets, like SOHO, Stereo, and even Hubble, aren't designed to capture fine plasma structure or tail modulation. If they didn't see the pulse, they can't comment on it. But this doesn't explain the absence of commentary on the other anomalies, like the unnatural tail shape or the missing debris field. Explanation 2, internal review. In many cases, NASA scientists will withhold public conclusions while peer review is underway. If they observe something anomalous, it's possible that internal teams are analysing the data, preparing papers, and waiting for confirmation before releasing anything to the public. But again, no placeholders, no teasers, no, we're looking into it, just static. Explanation 3, they don't want to go first. This explanation may be the most likely. With China's CNSA removing its raw telemetry and offering no statements, and ESA remaining silent, NASA may be choosing a cautious route. Don't lead. Let someone else say the strange thing out loud first. Because once a space agency publicly acknowledges an unknown, especially one with directional plasma pulses in an interstellar object, it becomes an international story. And international stories require answers. But what if NASA has none? What if all their models of tail behavior, cometary mass loss, or plasma dissipation fail to explain what they're seeing? That's not just a data problem. That's a paradigm problem. It forces them to question their assumptions, and doing that in public is risky. Then there's the more uncomfortable possibility they saw it, and they don't want to talk about it. Not because it's dangerous, not because it's alien, but because it's unexplainable, at least with current physics. And when institutions built on certainty encounter anomalies, the first reaction isn't panic, it's silence. Silence buys time to review, time to recalibrate, time to make sure it's real. And in that silence, speculation grows, forums light up, SETI threads ignite, whispers of propulsion, resonance, guidance. Theories that would normally be dismissed are now finding traction, because the agencies designed to dismiss them have gone quiet. This is not unprecedented. In the early days of pulsar discovery, researchers called them LGM, short for little green men, because the signals were so regular. It took months of private research before they confirmed a natural explanation. Rotating neutron stars. Could something similar be happening here? Possibly. But in the meantime, the quiet from NASA is deafening, and it leads to one unshakable question. If there's nothing to worry about, why is the most powerful space agency on Earth saying absolutely nothing? In the days following the pulse detection by Tianwen-1, a quiet reallocation occurred in Northern California. The Allen Telescope Array, SETI's primary radio observatory nestled in the remote shadow of Hat Creek, quietly shifted its scheduled observations. Without fanfare and without any public statement, it retargeted one of its L-band receivers and pointed it directly at the outbound path of 3I Atlas. No official announcement, no press release, just an updated observation log buried in the archive metadata. SETI was listening again. To understand why that matters, we need to understand what SETI is and what it isn't. SETI doesn't chase comets. It doesn't study ion tails or dust structures. Its mission is singular: search for extraterrestrial intelligence, specifically signs of technology. SETI doesn't waste time on solar system objects unless there's reason to suspect that object might exhibit non-natural behavior. So why did they pivot to 3I Atlas? It wasn't because they thought the comet was sending messages, it's because of what the pulse wasn't. The event Tianwen-1 captured on November 27th wasn't electromagnetic, it wasn't radio, it wasn't encoded, but it was rhythmic, directional, and, most importantly, it matched no known natural process. That's a flag. In SETI terms, this is what's called a candidate of interest. Not a signal, not a transmission, but a phenomenon that warrants secondary surveillance, just in case. Not because it's alien, but because it's anomalous, and anomalies are where SETI begins its work. The Allen Telescope Array, or ATA, is uniquely suited for this kind of follow-up. It's not a single dish, but a network. 42 antennas working together to form a synthetic aperture, giving it both sensitivity and flexibility. Unlike giant single-dish telescopes like Arecibo once was, ATA can pivot quickly. It can sweep an area of sky, divide observation time, and look for narrow band emissions across a wide frequency range. Within 48 hours of the pulse leak from China's scientific networks, ATA was observing the region surrounding 3I Atlas. Not for hydroxyl radicals, not for spectral dips, but for coherence, the kind of signal that doesn't occur naturally. This kind of move, while subtle, is profound, because it signals that SETI sees potential in the event, not certainty, but enough pattern, enough intrigue, enough mystery to merit resources. What were they hoping to find? Not language, not pulses, not a message in a bottle. They were listening for what SETI calls non-thermal coherence, signals that are structured in frequency, narrow in bandwidth, and persistent over time. In other words, the kind of radio emission that doesn't come from exploding stars, comets, or plasma waves. Something made. To date, no such emissions have been reported from 3I Atlas. But that doesn't mean SETI found nothing. SETI's protocol is conservative. It requires multiple observations from multiple instruments before any claim can be made public. If they detect something even slightly anomalous, it must be confirmed by a partner observatory, often one outside the United States. And so far, SETI is silent. Just like NASA, just like CNSA. But the reactivation of the queue speaks for itself, because observation time on arrays like ATA is limited. Competing proposals range from exoplanet surveys to pulsar timing experiments. Every second cost funding, labour, data storage, and processing power. And yet, 3I Atlas got a second look. That means the pulse detection was compelling enough to shift the priorities of the world's most targeted search for intelligent life. And if they're looking, we should ask why. And more importantly, what are they hoping to hear? We often talk about one-time events in astronomy. A rare flare, a sudden outburst, a rogue detection. These are anomalies, brief, spectacular, and usually over before we can aim a second telescope. But what if the event doesn't end? What if the pulse that Tianwen-1 detected wasn't a glitch, wasn't a one-off, but the beginning of a pattern? Because if the tail of 3I Atlas pulses again, and does so regularly, it stops being a mystery and starts becoming a system, and systems demand explanation. First, let's define what a repeating pulse would imply. In plasma physics, repetition signals feedback. Something inside or around the object is generating a cycle, accumulating energy, releasing it, then resetting. On Earth, we see this in natural systems like geysers, tectonic stress build-up, or even cardiac rhythms in biology. In space, it's rarer. Pulses spin and flash, yes, but they're dead stars, huge, fast, and governed by gravity. A comet doing this? That would be a first. If the tail keeps pulsing, then the outgassing, or whatever process is driving the emission, is regulating itself. That means some internal process is acting like a metronome, not an explosion, not a vent, not a collapse, a clock. So what happens next? Let's imagine three possibilities. Possibility 1, the pulses accelerate. This would imply increasing internal pressure. Perhaps thermal energy is building unevenly in the comet's structure, creating venting cycles that shorten over time. But if this were the case, we'd expect fragmentation, cracks, fissures, maybe even a breakup. And yet, 3I Atlas has shown no structural compromise. The object remains stable. Possibility 2. The pulses repeat with perfect timing. This would be more alarming. Rhythmic pulses that return at fixed intervals, say every 23 seconds for 3 minutes at a time, imply either a mechanical process or something interacting with an external field. Could the comet be resonating with solar magnetic harmonics? Could it be responding to orbital shears? If so, we should see the effect vary as its distance from the Sun changes, but we haven't. Which leads us to possibility 3. The pulses are communicative. Now, before jumping into science fiction, let's be clear. This does not mean alien contact, but in physics, communicative simply means informative over time. If the pulses change, grow longer, shorter, or vary in amplitude, they begin to carry data. That data could tell us about the interior of the object, the surrounding plasma environment, or even reveal the presence of structured material inside. At that point, 3I Atlas becomes not just an object to observe, but a phenomenon to decode. But what if the pulses don't repeat? What if they've already stopped? That leads us to a different kind of question. Were they a trigger? In engineering, a system often pulses once when it starts, when it boots. Think of it like a heartbeat at birth, a spike of activity, an initialization. If that's what we saw, then the pulses weren't the message. They were the startup. And if that's true, then something just turned on. In the next few days, astronomers will be scanning the tail for residual motion, looking for micropulses, energy rebounds, or phase lags. If even a faint echo appears, it will be treated as confirmation that we're not dealing with standard cometary outgassing. Because once something pulses twice, it isn't an accident, it's a cycle. And cycles have intentions, whether natural or not. So what happens if the tail keeps pulsing? We listen, we map the rhythm, and we prepare for a conversation we didn't know we'd started. Before we imagine machines inside a comet or whisper theories too loud, let's return to the star at the center of it all, our Sun. Because one of the most overlooked forces in deep space isn't an object, it's a rhythm. The Sun breathes, it pulses, it cycles through periods of magnetic expansion and contraction, emitting flares, gusts of solar wind, and shifting magnetic fields like a heartbeat spread across millions of kilometers. So here's the question. Could 3I Atlas be resonating with that rhythm? At first glance, it seems possible. Plasma is deeply responsive to magnetism. If the solar wind's periodic compression happened to match a structural frequency inside 3I Atlas, it could theoretically set off a resonance. Like a violin string vibrating in sympathy with a nearby note, the comet might be amplifying the Sun's signal. But when we say resonance, we need to be specific. In physics, resonance is when an external force drives a system at its natural frequency, causing oscillations of large amplitude. It's why a child on a swing needs just a tiny push, as long as it's at the right moment. It's why soldiers break step on bridges, and why wine glasses shatter when they meet the pitch of their own structure. Could something similar be happening here? Let's build a model. Imagine that 3I Atlas has internal chambers, pockets of gas or stratified layers of rock and ice that respond to external forces. If the solar magnetic field is fluctuating, say in 23-second intervals, and if that field passes through the object's tail, it might excite those structures. They vibrate, they flex, and suddenly the tail pulses. That would be remarkable, but still natural. However, there's a problem. Solar resonance isn't subtle. It usually spans hours or even days. Solar flares have cycles, yes, but not seconds. The idea that the Sun is emitting pulses every 23 seconds contradicts decades of solar observation. Even during high magnetic activity, the oscillations seen in plasma fields like alpha waves are typically broad, erratic, and not nearly this clean. What's more, if the Sun were causing this, other comets would show similar tail pulsations, but they don't. Even during similar orbital positions, when comets pass close to the Sun or cross active regions, we've never seen this behaviour. So we have two issues: timing and exclusivity. The timing doesn't match what we know of solar cycles, and the exclusivity, that only 3i Atlas is exhibiting this behaviour, suggests it's not the Sun that's unusual, it's the object itself. Still, let's not abandon the idea entirely. There's one more possibility. What if 3i Atlas isn't resonating with the Sun's magnetic field, but with its harmonics? This is a deeper idea. Just as musical notes have overtones, the Sun's activity might contain substructures, hidden frequencies buried within the chaos. If the object has a structure sensitive enough to detect those harmonics, it could resonate in ways we've never observed before. Not because the signal is strong, but because the receiver is perfect. That's a bold claim, but it's not impossible. We've seen resonance phenomena in the strangest places. The Moon rings like a bell after meteor impacts. Saturn's rings oscillate in response to its interior pressure waves. Even Earth has microseisms, vibrations in the ground that pulse in harmonic patterns from ocean waves. So why not a comet that hums with solar frequencies? Still, to accept this, we'd need to believe something astonishing: that 3i Atlas is built, not just randomly assembled, but tuned. Internally responsive to specific frequencies, and able to express that responsiveness as pulses in its tail. If that's true, then it's not just a rock with gas, it's an instrument, and the Sun, knowingly or not, is playing it. Before 3i Atlas, there was another anomaly. In April 2007, a faint but peculiar comet passed through the inner solar system. It was Comet C 2006 P1, better known as McNaught. And for a brief window, just a few days, its tail appeared to split in two. One portion streamed away from the Sun, as expected, but the other, almost impossibly, pointed toward the Sun. Astronomers called it an anti-tail. At first the term sounds wrong. Comet tails are shaped by solar radiation, particles pushed away by pressure. So how could a tail defy that force and point backwards? The answer lies in perspective. Anti-tails are optical illusions. They happen when Earth passes through the orbital plane of a comet's dust trail. From our viewpoint, the wide spread of slower-moving particles appears to bunch up in a narrow streak, aimed toward the Sun, when in fact it's simply trailing behind in a flattened sheet. The geometry creates the illusion of a second, backwards tail. But that's not the whole story. In several cases, McNaught included, the anti-tail appeared structured. Not just a haze or spread of debris, but a tight, coherent filament. And more importantly, the phenomenon didn't persist. It appeared, pulsed briefly, and then vanished. The reason we revisit this is because of one particular echo. The anti-tail of Comet McNaught twitched. In high-speed imagery captured by observatories in Chile, the anti-tail showed oscillations, minute fluctuations in brightness and density. At the time, they were dismissed as thermal distortion or turbulence in Earth's atmosphere. But a recent reanalysis sparked by the 3i Atlas pulse event found something disturbing. Those fluctuations were cyclical, not random, not noisy. They followed a subtle 23-second pattern, identical in frequency to the plasma pulse detected by China on November 22nd. This has led some astrophysicists to ask a difficult question. Was the McNaught anti-tail just a trick of light? Or was it an early sign, a prototype of what we're now seeing more clearly with 3i Atlas? If true, it would mean that what we're observing now isn't new, it's recurring, not just in time, but in form. That a subset of interstellar visitors, or even ancient solar system objects, occasionally exhibit tail structures that resonate, pulse, and defy expected morphology. And we missed it. Because we weren't looking for rhythm. We were looking for brightness, for mass, for speed. Not for behavior, but nature sometimes leaves clues in echoes. Here's where it gets even stranger. After Comet McNaught passed, its orbital path was recalculated with higher accuracy. What they found was a minute but real deviation. Its trajectory shifted more than expected. The cause was never definitively explained. No outburst, no fragmentation, just a clean, subtle curve in space. It was brushed off at the time, but now, with 3i Atlas exhibiting similar anomalies, tail stability, structured pulses, and a trajectory behaving outside expected non-gravitational models, the old McNaught data suddenly feels relevant. This isn't to say the two comets are the same. McNaught was not interstellar. It likely originated in the Oort cloud. But its behaviour shares a curious overlap with what we're seeing now, and that's the unsettling part. Because in science, repeated behaviour across vastly different systems demands a new model. Maybe these objects aren't as random as we thought. Maybe some are tuned, like instruments, built to resonate with solar harmonics, or to respond to something deeper. Or maybe we're only now learning to see what's always been there. The anti-tail wasn't backwards. We were. It began with a pulse, then came the silence, then came the tail, a structure that refused to behave like any natural comet we've ever observed. The trajectory didn't curve quite right. The wake was absent. The pulses repeated. And now, with every new observation, the same question begins to echo louder across observatories and labs. What is Thruot's Atlas? And more urgently, is it even a comet at all? Science relies on classification. When we discover a new object, we instinctively compare it to what we already know. Comets, asteroids, interstellar visitors. But 3i Atlas doesn't fully match any of those categories. It resembles a comet, but only from a distance. Up close, its behaviour is inconsistent, sometimes contradictory, and in some cases, entirely unprecedented. Let's list the disqualifications. First, the tail. Unlike natural comets, 3i Atlas's tail is narrow, stable, and lacks the expected turbulence of mass loss. It pulses, showing signs of controlled plasma emission rather than chaotic outgassing. Second, the structure. There is no confirmed nucleus fragmentation, no visible signs of erosion. Most comets, when subjected to solar radiation at this distance, begin to fracture, breaking apart or shedding large debris clouds. 3i Atlas remains intact, and not just intact, stable. Third, the motion. Its acceleration doesn't match known models. Minor but consistent deviations have been observed, and they do not align with what's expected from sublimation-driven momentum. It's as if the object is adjusting itself, not randomly, but in response to invisible forces. Fourth, the silence around it. Space agencies have gone quiet. Observations continue, but commentary has ceased. And that silence isn't because there's nothing to say, it's because there's too much. So we ask, is this a new kind of object? Not an alien ship, not a probe, but something between what we understand and what we haven't yet dared to define. One theory, gaining quiet traction in academic circles, is the idea of a non-biological information carrier. In simpler terms, an object built not to communicate with us, but to function in the background of the universe. Passive, silent, but triggered by proximity to stars like ours. Think about that. A structure, not built for us, not aimed at us, but simply passing through and responding. It wouldn't need to be alive. It wouldn't need to be intelligent in any traditional sense. It would simply need to be active, in a way we didn't previously associate with comets or interstellar debris. This leads to a new classification proposal, ARO, Autonomous Resonant Object. A body that does not emit constant signals or carry crew, but instead houses internal systems that react to star fields, gravity wells, or electromagnetic flux. It doesn't explore in the way we do. It listens, it samples, it records, and when the conditions are right, it pulses. This isn't science fiction, it's a model, and like all models, it can be tested. If 3i Atlas continues to emit pulses at regular intervals, if its tail geometry remains stable despite solar wind variation, and if its trajectory continues to shift in ways that suggest onboard mass redistribution, then we're no longer looking at an ice ball from another star. We're looking at category drift, the moment when an object no longer fits our boxes. And that's how science evolves. Not with a bang, but with a question that won't go away. What if this is not a mistaken observation? What if 3i Atlas is the first of its kind, or worse, what if it's not the first? It started as a cold interstellar wanderer, now it pulses, and in that silence the question grows, is something still guiding it? Drop your thoughts in the comments. What do you think these pulses mean? Are we looking at an anomaly or a system? Tell me your location and what time it is where you are. I read every comment. And remember, The deeper we look into 3i Atlas, the less natural it becomes. Until next time, stay curious.